Well, here's where we are so far. This is, you know, we're starting out with a lot of just mathematical preliminaries. We haven't done any dynamics yet. But here's where we are in the math preliminaries. We started out by talking about differential equations and separation of variables, which is the technique we're going to use for solving ordinary differential equations. So now we're done with that. The rest of the stuff is going to take a lot less time to deal with, and I'm going to deal with all the rest of it in this lecture. But here are the things we have to talk about. Derivatives of vectors. The product rule. And the chain rule. And all of these things deal with functions of one variable. In our case, remember our one variable, our one independent variable is always going to be time, and I suppose it's probably worth saying. So, you know, there's a lot of variables running around, but we're talking about functions of one independent variable. And for us, that's time. Okay, so let's first start by talking about derivatives of vectors. This is going to come up a lot, probably most often because of the two following relationships. Velocity is equal to the derivative of the position vector. The acceleration is the derivative of the velocity vector, which is the second derivative of the position. Also, the angular acceleration vector is the derivative of the angular velocity vector. One thing that's going to be a current running through this whole class is this relationship gets complicated if the coordinate system is rotating. And at the end of towards the end of this class, we're going to be seeing how to deal with these relationships when the coordinate system is rotating. But in an inertial coordinate system, you're used to these relationships, and this is where these derivatives are going to come up. Okay, so say that you have a vector. So you have a vector u. You want to take the derivative with respect to time, and u is a function of time. You can write this a couple ways. But the way you do this is you just take the derivatives of the components. So the derivative of the x component, the derivative of the y component, and the derivative of the z component. Okay, so that's how you take that derivative. It's just, in 3D, it's just 3 separate derivatives you have to take. In 2D, it's 2 separate derivatives. So here's an example. In an inertial coordinate system, let's say that your velocity vector is t squared 5t and cosine of t. Oops. And you want to know what the acceleration vector is as a function of time. Well, the acceleration vector is just the derivative of the velocity. So you have the x component is the derivative of the first component of the velocity. The y component of the acceleration is the derivative of the y component of the velocity. And the z component of the acceleration is the derivative of the z component of the velocity. Sine t negative. Okay. So there's no cross stuff going on. You just, one by one, deal with the independent components. Okay, the next thing we have to be on the same page about is the product rule. I guess this, in our numbering, so this is number 3. And there are a few ways this comes up. Probably in calculus, you saw it mostly in terms of just a scalar times a scalar, taking the derivative of that. But I just want to be clear that, you know, this will come up in a few different ways. First, what if you have scalars? So what's the derivative of the quantity x times y, where x and y are scalars? Another way this is, you see this sometimes, is with a bar over the x and y and then a dot saying the time derivative. Well, the product rule, and again, this is the one you're probably most used to. You got x dot times y plus x times y dot. Similarly, if you have a scalar times a vector, what do you do to take the derivative of, you know, say x times v, where x is a scalar, v is a vector? Again, you could write that as this. Well, the rule is really the same. You have the derivative of the scalar times the vector plus the scalar times the derivative of the vector. And then we have two vector products, two types of vector products, the dot product and the cross product. So for the dot product, say we have the vector u dotted with the vector v, and we want to take the derivative. This is the derivative of u dotted with v plus u dotted with the derivative of v. Notice that this term will give you a scalar, this term will give you a scalar, add them together and you get a scalar out of this. The last one we need to do is the cross product. And notice that these have all had a similar form. It's derivative of the first times the second plus the first times the derivative of the second. And that's going to keep going with the cross product. So say you want a time derivative of u crossed with v, where those are both vectors. That's going to be u dot crossed with v plus u crossed with v dot. Okay? Let's do an example to show how this works with the cross product. I'm not going to go through an example of each one of those, but what's the derivative of cosine of t, sine of t, 0, crossed with 0, 0, t squared? And of course, notice that the way we're going to do it, you could also just take the cross product now and then take the derivative of it and of your result, and you should get exactly the same thing that I'm going to get using this product rule. So this gives us, so we want derivative of the first times the second. So negative sine t, positive cosine t, 0, crossed with the second, plus the first crossed with the derivative of the second, so 0, 0, 2t. Multiply out these cross products, and you get t squared cosine t plus 2t sine t. So that's the first component. The second component, t squared sine t minus 2t cosine t, 0. And again, you could check this. You could multiply out the original vectors and then take the derivative of that result, and you should get this same thing. So there's one thing I want to point out, because it's sort of like a, it's not that bad. I was going to say it's like a train coming in the distance. It's sort of probably the most confusing thing in this class. It's not really all that bad, but is later on when we deal with rotating coordinate systems, we're going to have to deal with the fact that time derivatives we have to treat differently. And so I just want you to sort of notice this, get used to the idea that this is going to be an issue in this class. Any vector, I don't mean this specifically as the velocity vector. Maybe I'll write it as, let me change that to the vector u, is equal to x times, the I unit vector plus the y component times the j unit vector plus the z, the magnitude of z times the k unit vector. And so notice that the product rule says u dot is equal to x dot I plus x I dot plus y dot j plus y j dot plus z dot k plus z k dot. Okay. When you have an inertial coordinate system, you don't have to deal with this term or this term or this term, right? Because the unit vector I, the unit vector j, and the unit vector k don't change. But if the coordinate system is rotating, all of a sudden these terms become non-zero, and that's why taking time derivatives in a rotating coordinate system, needs to be dealt with in a totally different way. What you're doing is all of a sudden you're having to deal with I dot, J dot, and K dot. And that's sort of an intuitive like understanding of why rotating coordinate systems are going to give us trouble coming up. The last thing we need to talk about is the chain rule. And the idea of the chain rule is this. If you're taking the derivative of f, which is a function of all these things, x, y, dot, 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 z. But really, x, y, and z are all functions of something else. In our case, it would be t. Then how do you take this derivative? Well, you do it as the partial derivative of f with respect to the first one times the derivative of the first one with respect to the independent variable plus the partial with respect to the second one times derivative of the second with respect to time, and on, you know, there could be 100 of these. df dz times dz dt. An example of using this is so find the derivative of f with respect to time, where f is a function of xy equal to x squared plus xy. And I'll give you the values, the functions for, so x is equal to t squared and y is equal to sine t. Okay, so notice the first thing you could do is you could just take these functions, plug them into f right now, and then take the time derivative. You know that that'll work. So the method that I'm giving, this chain rule method, needs to give us the same answer as that. And if you have the time, I would, recommend doing that. Take these, substitute them into f, take the derivative, and make sure that the answer we get is the same thing. Okay, so by the chain rule, df dt is equal to the partial of f with respect to x times dx dt plus the partial of f with respect to y times dy dt. The partial of f with respect to x is 2x plus y, so 2x plus y. The derivative of x with respect to time is 2t. Now we're on to this second term. The partial of f with respect to y is x. The derivative of y with respect to time is cosine t. And so if you multiplied this out and substituted the functions of x and y in for the values of x and y here, you need to get the same thing out as if you did that substitution before you took the derivative, and you would. Okay, one thing I want you to notice is, so this is an important thing going forward. The chain rule is often going to come up in dynamics this way. So it often comes up like this. We already know, so this is nothing new, that A, the acceleration vector, is equal to d dt of the velocity. So now suppose that you're not given the velocity as a function of time. You're given the velocity as the function of the x position. So suppose you're given v as a function of, x. Well, x really is a function of time, but suppose you don't know what that function is, okay? And say this is like the x component of the position. Then you can think of the acceleration as the derivative of the velocity with respect to x times the derivative of x with respect to time, and that is the derivative of the velocity with respect to x times the x component of the velocity. Okay, things like this will come up where we actually, even though sort of implicitly we're taking a derivative with respect to time, we don't even have to know what that function of time is. So this is something that you should look for whenever you want to take a time derivative to get the answer, but you're not given the function in terms of time. See if you can figure out a way to work this chain rule to make that happen. Here's an example of doing that. So say that the velocity is given as x squared 2x. That's the velocity vector. And notice it doesn't say anything about time. And we want to know what's the acceleration vector when x is equal to 5. Well, we know the acceleration vector is the derivative of v with respect to x times dx dt, and the derivative of v with respect to x is 2x 2. The derivative of x with respect to t is the x component of the velocity, so that's x squared from what we know about the velocity. And so we get an acceleration vector that's equal to 2x cubed 2x squared. Now if we want to evaluate that, we're asked to evaluate that when x is equal to 5. Just plug 5 in there and we get 250, 50. So in essence, we took the time derivative of the velocity without ever knowing a function, without ever knowing what the function was in terms of t.